Hello everyone, welcome back. So today we'll be discussing your different functional forms of regression models. Okay, so till now we have seen the linear form of regression models. Okay, so those were simple forms. So now uh, we might be visiting some other forms of the regression model because uh, every time that you run a regression, so the model might not be as simple as you have seen till now. So you'll have to make certain transformations over there, and then you'll have to work with the model. So there are a couple of models that we'll see. So we'll start with your log linear model. So the advantage of this model is that it allows us to measure the elasticity of one variable over the other. Okay, so let's start. So consider the following exponential regression model. So this is a model, a regression model. So it is in the exponential form. Okay. So if you see this model, you will have to figure out how to work with this model. So the basic idea is to simplify the model, to bring it to a form that is more accustomed to my understanding. Okay, that is the linear form. So the way I have seen the regression equations till now, that is your yi equal to beta 1 plus beta 2 xi plus ui. So I'll try to bring this regression model into this form so that I am familiar with the model and I'm able to work with it. So what I'll do is I'll take log on both the sides. Okay, so this transform to ln yi, that is the natural log, is equal to ln beta 1 plus beta 2 ln xi plus ui. So since both my variables here will be in the log form, that is why this is also called your log log model. So I've given the names here. So this is also called your log model, or your double log model, or your log linear model. Log linear model because your variables are in the log form, but your parameter is linear. Okay, so that is why it is also called your log linear model, right? So lny, so this is, so I have replaced ln beta 1 by alpha because this will also be a constant term. So I've used a simpler notation for it. So the equation or the regression equation looks even more simpler. Okay, so ln yi is equal to alpha plus beta 2 ln xi plus ui. So this is called your log double log or log linear model. So if this equation, or if this regression equation, if in this equation the assumptions of your classical linear regression model are fulfilled, then the parameters, okay, can be estimated using your ordinary least square methods. Okay, so now I've written your I've transformed this equation even more further to look even more alike to the regression equation that we have been reading till now, that the normal regression equation. Okay, right? So I've used different notations here where yi star represents your lni variable, ln yi variable, and your xi star represents the ln xi variable. Okay, so using this equation and using your ordinary least square method, you can estimate your beta 2. Okay, right? Or beta 2 hat. You can estimate your beta 2 hat. That would be a estimator of your true parameter, right? So let's try to understand what this means in the practical sense, or what running around a regression that is of the exponential form using the log model looks like. Okay, so this is, suppose we have a function or regression equation which is like beta 1 xi to the power minus beta 2. So your y variable represents the quantity quantity demanded, and your x variable is representing the price. So it is basically a equation that shows the relation between the quantity demanded and the price of a commodity, right? So if I plot this on the graph, so I'll get a graph like this, a downward sloping graph. Okay, so this is the normal pictorial representation of the equation, and if I take the log of this equation and then I plot this on on a graph, then I'll get a graph that is of a straight line, that looks like a straight line. Okay, so this is your log of quantity and this is your log of price on the y and x variable x axis, and this is the straight line equation that you get by plotting the log of this equation. Okay, so uh, this is the logarithmic transformation and this is the change that you see. So from a downward sloping graph you get a straight line which is also downward sloping. So now how do I estimate, or what is the significance, or how do I interpret my beta 2 here? Okay, let's see this. So this graph will really help you and get an idea, to help you get an idea. Okay, so beta 2 is basically the slope coefficient of the regression equation, right? We know this. Okay, so this is my equation that I had taken from here. Okay, so I've taken a log of that equation, working on that equation. I've taken a log of that equation, and then if I differentiate both the sides, this is what I get. So del ln y upon del x is equal to 0 because this is a constant. So its differentiation would be 0 minus beta 2 into del ln x upon del x. Okay, so differentiating ln y, I get 1 upon y del y upon dx del x, which is equal to minus of beta 2 into 1 upon x, because the differentiation of ln x would be 1 upon x only. So if I interchange, I'll get beta 2 is equal to x upon y del y upon del x, where your y is the quantity and x is the price. So this formula looks similar to a quantity that we have already read in the economics lessons. Okay, so we'll see what this is. We'll see. So we have learnt about elasticity, or your price elasticity of demand for this given equation that we are working on. So it is basically the percentage change in quantity demanded upon percentage change in price. So if y is your quantity and x is your price, if I use this formula, I get elasticity is equal to this thing, x upon y del y upon del x, which is equal to your elasticity. So if I go back and compare, this is the this formula is same as this formula. So it means that my beta 2 is actually representing the elasticity. Okay, it's measuring the elasticity of y, that is my quantity, with respect to x. Okay, so if x is changing, how much is y changing? Okay, what is the impact of the changes in x on y? That is being captured by my beta 2. So basically this is for small changes, because ln x is basically a representation of small changes. Okay, so this applies for small percentage changes in your x and y variable. Okay, so when there is a small change in your x and y variable, so your beta 2 is basically representing your elasticity, right, of the y variable with respect to x variable. So this is the interpretation of beta 2 here. So that is why this model is used very significantly in a lot of uh, calculations, because it allows us to measure the elasticity. Okay, how elastic is the y variable with respect to the x variable. So if I allow for a certain change on the x variable, how much change, percentage change, I can expect in the y variable. So that is where this model comes really handy. Okay, uh, yeah. So a feature of this model is that the log-log model assumes that the elasticity, that is your beta 2 or your slope coefficient, remains same throughout the model, and that is why it is also called your constant elasticity model. So just try to remember this, that it assumes, as we had seen, that the graph here turned out to be a straight line graph. It means that the elasticity is constant everywhere. Okay, the rate of change, or the percentage rate of change, is constant everywhere, and that is why it is also called your constant elasticity model. So I hope you understood the model, and I hope you could really appreciate how useful it can be, okay, in the practical sense. So this was all for this video. So we'll work with a different model in the next video. Until then, take care and see you soon.